Hey friends, I want to talk today about irreducibility, which is chapter 11 in the book that we're following. And I want to start by remembering some things that we know about irreducibility. We are starting in a polynomial ring. So given a field F and a polynomial P in F bracket X, we say that P of X is reducible, provided we can break it up in as a product of polynomials of smaller degree. So let's get that recorded. We say P of X is reducible, provided there exist F and G polynomials in F bracket X, where P equals FG, and the degree of F is strictly less than the degree of P, and the degree of G is strictly less than the degree of P. And we should probably specify that we want a non-zero polynomial here, because our convention is to say that the zero polynomial has degree negative infinity, and I don't really want to argue about whether negative infinity is less than itself or not. So we're going to only worry about non-zero polynomials and whether or not they are reducible or irreducible. If it's not reducible, we're going to say P of X is irreducible. And let's think about what it would mean to logically negate the definition of reducible. It means that for all F and G in F bracket X, where P equals FG, either the degree of F is equal to the degree of P and the degree of G is 0, meaning that G is a constant polynomial. So all we did was pull a constant factor out, or vice versa, or the degree of G is the degree of F, or sorry, the degree of P, and the degree of F is 0. That's what we mean by irreducible. We can't actually factor this into a product that's interesting. The only way we can factor is by messing around with constants, which it doesn't really feel like it should count as factoring. And when I say reducible and irreducible, I mean over the field F, right, into polynomials with coefficients in F. If we think about factoring things into polynomials with coefficients in the complex numbers, the fundamental theorem of algebra says we can always factor into degree 1 terms. So if your degree is 2 or higher, you're going to be reducible over the complex numbers. But if we're thinking about reducible over the rationals, we may not be able to find a polynomial with rational coefficients that is a nice factor. And we're going to see some examples of that. I also want to remind you of a proposition that we've got that tells us about reducibility for polynomials of small degree, which is nice if we have polynomials of degree 1, 2, or 3. And the last thing we'll do is look at an irreducibility criterion for polynomials of larger degree. So let's recall proposition 8.12, which says that if we let F be a field and we take a polynomial in the polynomial ring F bracket X, then we've got some things happen. If the degree of P is 1, then P is irreducible over F. So degree 1 polynomial, the only way we're going to be able to factor that is by messing around with constants, because we know that the degree of a product of polynomials is the sum of the degrees of the factors. And so if we need things to add up to 1 and we're allowed to use 0, 1, 2, et cetera, well, the only way to do it is to take 0 and 1. That means that we're really interested in degree 2 or higher for irreducibility. Like that's where the question starts to get interesting. So if the degree of P is less than or equal to 3, which is going to subsume the degree equals 1 case, but it's okay, then P is irreducible if and only if P, I should say, sorry, irreducible over F. If and only if there exists, let's say if and only if P of X equals 0 has no solutions in F. Right, that's saying that there are no roots of this polynomial that belong to the field F. And we proved this. There's another video that we did asynchronously in this class where we proved that this is the case. But the gist of this is if you take a degree 3 polynomial and you find that it's reducible, that means that it's going to have a factor of degree 1 and degree 2. That's the only way that we can find factors that are both that both have degrees smaller than 3 that will add up to 3. The degree 1 factor means you've got a root. Same thing with degree 2. The only way that we can do this in degree 2 is to have degree 1 and degree 1, which means that, again, if you're reducible, you've got a root. And if you're irreducible, you can't have a root because there's not going to be a degree 1 factor. This breaks down for degree 4 and higher because we could have reducible polynomials that factor into 2 irreducible pieces of degree 2, and those don't tell us about the roots in F. So this is really strictly about showing that polynomials of small degree 1, 2, or 3, are irreducible. So we've got to bump up to some better examples. To some better criteria. So let's look at Eisenstein's irreducibility criterion. That's the theorem that I want to talk to you about today. Eisenstein's irreducibility criterion. It's easy to mistake this for Einstein, but my mnemonic for remembering it's Eisenstein and not Einstein is that Einstein actually wasn't a really great mathematician. So it's unlikely that he would have had a proposition like this. In fact, it's probably somebody else. So, and I'm joking a little bit, but it did take Emmy Noether to actually prove some of Einstein's mathematical results. So Eisenstein, not Einstein here, his irreducibility criterion. And what it says is this. We're going to let f of x be a polynomial with rational coefficients that actually has integer coefficients. And we'll do an example that shows, what to do if we don't have integer coefficients, how to fix up our polynomial. And we're going to write it as f of x looks like a n x to the n plus a n minus 1 x to the n minus 1 plus blah, blah, blah plus a1 x plus a0. And I keep forgetting to include the hypothesis here, but we want a non-zero polynomial in order to do this. We don't want to be working with the 0 polynomial. We're then going to think about prime numbers and how they might relate to this polynomial. So I'm going to let P be a prime number. Actually, let me say it this way. Sorry, I'm unhappy with the way that I'm stating it here. So if there exists a prime P for which the following happens. P doesn't divide the leading coefficient. P does divide all the other coefficients. So the constant, the degree 1 up to the degree n minus 1 coefficient. And P squared does not divide the constant coefficient then F is irreducible over Q. And we're not going to cover the proof of this, but the proof is actually really lovely. I'll say a couple words about the proof, not the actual proof. The proof uses something called Gauss's lemma. And it actually takes us back to working mod P. So we could do this working mod modulo the prime P. And what I'll do at some point is I might make a video that goes through that proof just to tie in our integers mod P again. But at this point in the course, what we really want to do is we want to use Eisenstein's irreducibility criterion to argue that some polynomial is irreducible in order to have a minimum polynomial for something. So then we can talk about the degree of the field extension and blah, 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 blah. All right, so let's cook up some examples here. Let's look at m of x is x to the 5th minus 7, which definitely belongs to Q bracket x. In order to use Eisenstein's irreducibility criterion to argue that this polynomial of degree 5 is irreducible, I need to find a prime P that does not divide the leading coefficient. So our leading coefficient is 1. We have a monic polynomial. Our remaining coefficients, there's only one, it's the constant one, -7. And the constant coefficient is 7. And so if I look at Eisenstein's irreducibility criterion, what I'm looking for is a prime that doesn't divide 1. Okay, fine, any prime's going to do that. A prime that does divide -7, it's probably going to be 7. And a prime whose square does not divide 7. And it turns out 49 does not divide 7. So to use Eisenstein's irreducibility criterion, we're going to take P equals 7. And we check, we have P does not divide 1. P squared does not divide 7. And P does divide -7. And so applying Eisenstein's irreducibility criterion, we see that this polynomial is irreducible over Q. So if I were writing this up, I would say by Eisenstein's irreducibility criterion with prime P equals 7, we see x to the 5th minus 7 is irreducible over the rationals. So that's pretty handy. That's nice. Let me make up an example. Let me talk through how I would make up an example of an irreducible polynomial that is irreducible because of Eisenstein's criterion. So let's say that I've got our polynomial called f of x. This is another example. I'm going to pick the prime that I want to use. First of all, let's say that I want to use the prime. What prime do I know some powers? I don't know, prime, let's take 5. So in the back of my head, as I'm making up this example, I'm like, all right, I'm going to use the prime 5. I want to make sure that my leading coefficient is not divisible by 5, and my constant coefficient is divisible by 5, but not 5 squared. So I don't want it to be divisible by 25. So I'll make my constant coefficient 15. That seems fine. Add some other multiples of 5 in the middle. Let's make my leading coefficient. I'm going to make it a fraction to show you what to do if we've got some fractions. Make it 1/3 x to the 4th, let's say, minus 10 over 3 x cubed plus 25 over 6 x squared plus 5x plus 15. All right, so I want to use Eisenstein's irreducibility criterion to prove that this is irreducible over Q. I know that I can't use proposition 8.12 because my degree is too big, right? My degree is 4. So the trade-off with proposition 8.12 is I can work over any field, but my degree has to be small. With Eisenstein, I can work with any degree, but I can only work over the field of rationals. So there are some trade-offs either way. One of them lets us deal with any field but small degrees. One of them lets us deal with high degrees, but a very specific field. So I want to think about this thing. I can think about f of x. I can make a related polynomial g of x, which is going to be 6 times f of x. If we write that down, that's going to look like 2x to the 4th minus 20x cubed plus 25x squared plus 30x plus, oh dear, 15 times 6 is going to be, 6 times 5 is 30, so 90, I think. That feels right. Let's say it's 90. And my claim is that g of x is irreducible if and only if f of x is. Sorry, I'm trying to write over here, but my cat is obviously sitting on the iPad exactly where I want to be writing. So let's see what happens. So if f of x is irreducible, so let's see g, I don't know, let's do first g is irreducible. Actually, let's do g is reducible. We'll do the contrapositive of both directions. So do the backwards direction by contrapositive. G is reducible implies there exist P and Q in Q bracket X, where G equals PQ, and the degree of P is less than the degree of G. Degree of Q is less than the degree of G. And that implies that 6F is 6 times PQ. Degree of F and degree of G are equal. And therefore, if I use these factors PQ, both of the factors have degree less than F, which means that degree of P is less than degree of F. Degree of Q is less than degree of F. Which tells us that F is reducible. And in fact, that is an if and only if. So if I found those things where I could reduce, I guess we'll do both ways by the contrapositive. If I find these polynomials where I can factor G, I found the polynomials where I can factor F, and vice versa. So it's a really short argument to say, like, okay, if I need to multiply by an integer constant to clear denominators, that's not going to affect the irreducibility of my polynomial. So we can, in fact, really use things that have fractions and then just get rid of, like just multiply by the least common denominator or something like that to get rid of all the denominators that we need to worry about. Okay, so now I'm in a situation where I've got a polynomial, I've got integer coefficients. I want to use Eisenstein's irreducibility criterion. So my leading coefficient is 2. My remaining coefficients in a list are -20, 25, 30, and 90. And my constant coefficient is 5. So no, it's not 5. I mean, I kind of know that I want to use that prime, but let's work it out here. My constant coefficient is 90. So here's what I'm looking for. I'm looking for a prime that does not divide 2. There are lots of those. I'm looking for a prime that does not divide 90, or a prime that squared does not divide 90. Again, also lots of those. And that prime should divide all of the coefficients for -20, 25, 30, and 90. So looking at those coefficients, I can actually eyeball pretty quickly. There's only one prime that's going to work. The 5 works because it divides all of those. 3 doesn't divide 20 or 25. 7 doesn't divide any of them. So, I might have to do a little bit of poking around to decide. Maybe I decided I wanted to try 3. Well, bummer, 3 squared divides 90. So that's not going to be the prime that I want to use if I'm trying to make sure that my constant coefficient is not divisible by that prime squared. So after a little bit of visual inspection, maybe some scratch work on paper, I see that I could take P to be 5. So I would say by Eisenstein's irreducibility criterion with prime P equals 5, g of x, and hence f of x, by the little result we just proved, is irreducible over Q. All right, I want to do one more example, but I actually am going to pause the recording for a moment, if I can find where my little bar went, so that I can make sure all the arithmetic works out, because I didn't check it yet. All right, we're back. I want to do an example here where I look at this polynomial f of x, that's x to the fourth plus x cubed plus x squared plus x plus 1 in q bracket x. And if you're scratching your head thinking, how the heck does this have anything to do with Eisenstein's irreducibility criterion, I don't blame you, because I'm looking at this and I'm like, all of my coefficients are 1. There are no primes that divide 1. So I want to do something a little bit like what we did in the previous example and manipulate this polynomial to try to cook up some primes that are going to be mixed in here. So I'm going to work with a related polynomial. I'm going to take g of x to be f of x plus 1, right? I want to plug in x plus 1 wherever I had seen an x. And what I'm going to do, or actually what I'm going to defer to you to do in a writing assignment, but it's fairly quick, like the last one we did, is claim that g of x is irreducible if and only if f of x is irreducible. So if we make this substitution, it doesn't really affect the degrees of the factors that we're going to be able to find. So that's a little, we'll call it a lemma. And you're going to work on that on the next writing assignment. So when I plug this in, I'm going to get some stuff that I've got to, I'm going to take that x to the fourth, and I'm plugging in x plus 1. I'm taking that x cubed, I'm plugging in x plus 1. I'm taking x squared, I'm plugging in x plus 1. I'm taking x, I'm plugging in x plus 1, and then I have a plus 1. So let's plug all of that in. X plus 1, x plus 1, x plus 1, x plus 1. Now, back in chapter, 1, when we were messing around with binomial coefficients, we figured out what we need to do if we're going to take, x plus y and raise it to the nth power. We end up getting those binomial coefficients in the middle. And many of you recognized that we end up with the rows of Pascal's triangle. So one way to quickly work this out, we have Pascal's triangle, named for Blaise Pascal, although I'm sure he's not the first one to observe this. I'm sure it's just a relic of the fact that we only name things after Western mathematicians, which we should stop doing. We should actually get some other names in here. Anyway, if we look at Pascal's triangle, it starts out with like 0, choose 0, which is 1. And then we have 1, choose 0, and 1, choose 1. Both of those are 1. And then we know how to get the middle of the triangle. We had this lemma that that I proved that you used that said if I take 1, choose 0, and 1, choose 1 and add it up, I'm going to get 2, choose 1. So that's going to give me 2. And then 2, choose 0, and 2, choose 2. Both of those are 1. And so we can keep filling in our binomial coefficients as we go along this triangle. And if I clean it up a little, it looks like 1, 1, 1, 1, 2, 1. 1, 3, 3, 1, 1, 4, 6, 4, 1. And that's about as far in the triangle as I'll need to go to get all of my binomial coefficients to work out. So I could think about this as being when n is 0, when n is 1, when n is 2, these are the possible binomial coefficients. When n is 3, these are the possible binomial coefficients, n equals 4. So if I expand out x plus 1 to the fourth, using Pascal's triangle, what I'm going to end up getting is x to the fourth plus 4x cubed times 1. So I'm going to omit the 1, plus 6x squared times 1 squared. Again, I'm going to omit the 1, plus 4x times 1 cubed plus 1. So that expands out that first step for me. And then I'm going to expand out the x cubed, and I'm going to get x cubed plus 3x squared plus 3x plus 1. I'm going to expand out the x squared, and I get x squared plus 2x plus 1. And then I get x plus 1. And then I have my last lonely leftover 1. So let's see what we get when we actually add all of this up into our new polynomial. So when I add up the ones, I've got 1, 2, 3, 4, 5 ones. So my constant term is 5. Maybe that's the prime that I want to use. I've got a prime that divides 5, but 25 doesn't divide 5. So I'm thinking 5 is the p that I'm going to try. But I want to make sure the other coefficients up to the leading coefficient at our and excluding the leading coefficient are divisible by 5. So let's see. So I take 4 plus 3 plus 2 plus 1. That's 10x. So far, so good. 6 plus 3 plus 1 is another 10. So I get 10x squared. 4 plus 3 is 5. So I get 5x cubed. And I get an x fourth as my leading term. X to the fourth is my leading term here. And I see that this polynomial is like custom made almost to work with Eisenstein's irreducibility criterion with prime p equals 5. So I see that for this set of polynomials, p equals 5 is going to work. For the constant term, p squared doesn't divide 5, right? 25 is not an integer divisor of 5. And my leading coefficient is 1, and p doesn't divide 1. So by Eisenstein's irreducibility criterion, with prime p equals 5, g of x, and hence our original polynomial f of x, is irreducible over the rationals. Now, why do I care about this polynomial? I mean, I care about all polynomials because I'm a lover of polynomials, but why do you care about this polynomial? Well, it turns out it's the minimum polynomial of zeta 5. So this is something that you proved. Zeta p is a root of x to the p minus 1 plus x to the p minus 2 plus blah, 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 plus x plus 1. In this case, our p was 5, and that means that the minimum polynomial for zeta p over the rationals is a degree 4 polynomial. And that tells us how to build the extension field of Q, where we're throwing in zeta 5 and we're making sure it's a field. We're going to get all the way up to zeta 5 cubed in that extension field. And so what we might be able to do, and in fact, what you will do in the final paper, is you will show that if you take this polynomial, x to the p minus 1 plus x to the p minus 2 plus blah, 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 if you sub in x plus 1 for x, you get a polynomial where you can use Eisenstein's irreducibility criterion with prime p to show that it's irreducible. And hence, the original polynomial, this x to the p minus 1 plus x to the p minus 2 plus blah, 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 plus x plus 1 is also irreducible. And therefore, we know the minimum polynomial for all of our zeta sub p, where p is prime, which is pretty rad. That's a very useful result to us. So stay tuned. That's something that you'll work on your final paper. The last thing I want to mention is there are lots of other tests for irreducibility over different fields or with different criteria or for different degrees. The one that you might want to look up and have at your fingertips is called the rational root theorem. It's really nice. Some of you used it on a recent homework. It tells you what, if you have a polynomial with integer coefficients, it tells you what the possible rational roots might be. And it says, so take like all the divisors of the constant coefficient, divide by all possible divisors of the leading coefficient, and that cooks up your list of candidates. And then to check if those are roots, you just plug them in. So this helps you decide whether something has roots. If your degree is 3 or smaller, that will then help you decide using proposition 8.12 whether or not something is reducible. Again, doesn't work for degree 4 or higher because the roots, not having roots doesn't tell us about irreducibility. And that is a wrap for chapter 11. I will see you folks next week. We will start getting into chapter 12, which brings back some linear algebra. The stuff that you might want to take a look at and review a little bit is the idea of a basis for a vector space, which is a set that is linearly independent and also spans all of the vectors in the vector space. And related to the idea of a basis is the idea of dimension. And those are the things that we're going to use in class next week to learn even more about extension fields. That's a wrap. Stop recording. Why is it so hard? Okay.